No probs. Yeah, so we've already started the webinar just because of the errors that we were getting before you joined.
Yeah, yeah.
So yeah, I'll just quickly say yes, thank you for everybody joining today. We're joined by Dr. Raghav Pant from the University of Oxford. We've been working with Raghav and his team since June 2023 when the NIRD project started. This stands for Building Systemic Resilience of Independent Infrastructure Networks at the National Scale. If you have any questions throughout the session, please use the Q&A function and we will answer these in the end. I'll hand over to Raghav, who will be able to give you a better and deeper project deep dive and the results. So have you got some slides there, Raghav, that we can share on the screen, please?
Yes, sure. I'll just share my thanks a lot, Katie, first of all, for the introduction, and great to speak at the DAFNI seminar. So I'm just sharing my slides. I hope people can see the slides. I'll just put it on slide mode. Can everybody see
Yes, I
the
can
slide? Yeah.
click allow on that
Yeah.
request. There you go. Yeah,
Okay.
cool.
Thank
All
you so
yours.
much. Thank you so much. Thank you so much again to the Daphne team for giving me this chance to talk. So the project is called National Infrastructure Resilience Demonstrator, or NIRD for short. And I'm going to talk about some work we have done on stress testing road networks against extreme floods in Great Britain. This work is a collaboration with several other colleagues, and in particular, my colleague Yue Li, who's the lead postdoctoral researcher on this. I'm the principal investigator of this project. So Yue and I have done a lot of work together on this project, and a lot of this is the work of Yue that I'm presenting over here. So what I'm going to cover in this presentation is the background and motivation of our study, the aims and our methodology. I'll give you some demonstration of this work through some sample kind of case studies, and then I'll discuss the project outcomes and then ongoing and future work. So first of all, just to give a background about kind of us. So I am based in Oxford University in the Environmental Change Institute and work within the Oxford Program for Sustainable Infrastructure Systems. This program has been going on for a number of years. It's led by Professor Jim Hall, who's the current president of the Institute of Civil Engineers as well. And we work on the broad topic of infrastructure, sustainability, and risk and resilience. And we not just look at transport, which I'm going to talk about today, but other infrastructures like energy, transport, and telecommunications and everything. And we look at this at the global scale. So for the project that I'm going to talk about, our background and our motivation essentially comes from the fact that we are seeing increased flooding in the UK. And everybody, I assume, who's in this call knows this or is experiencing this already. So we've seen heavy rains and floods. Pulled some BBC news articles, which show as quite recently heavy rains and floods happening. I think the first news article is from Suffolk in England, and the second one is from Scotland. And we see the common theme is that rains are becoming more intense and essentially more flooding is happening. And this is kind of supported by the evidence from the Met Office, which shows that the annual rainfall amount, the change in rainfall amount from 1991, from 1996 till the 1990 time frame, the change from that all the way till now, which is 1991 to 2020 time frame. The map over here shows the change, which is the more blue you see over here, the more blobs of blue you see. That means an increase in rainfall compared to the last in the last 30 years compared to the 30 years before that. And not surprisingly, the evidence is clear that rainfall is increasing a lot. And along with all this increased rainfall, we see that there's a lot of floods that are happening. And some of the kind of evidence that has come through in terms of numbers, like how much is being spent. So the Office of Budget Responsibility estimated that the UK spent 125 million pounds to cope with the floods of summer of 2007. And this increased to 287 million for floods in 2015, 2016. And I'll talk about some of these later in my slides. But the evidence over here is that things are becoming more extreme, and with more extreme, there's also more costs involved in widespread flood disruptions. And the thing that we're also seeing that while all these large-scale assessments that are being done and a lot of kind of big flood events happen, which have happened over the last few decades in the UK. There's a lot of kind of evidence reports that come out of from the government. There's 3 reports that I've shown over here. The first one is from the summer floods of 2007. The second one is from the floods of 2013, 2014. And the third one is from the Environment Agency, which estimates the floods, cost of floods for 2015, 2016. And this is the total cost of floods. It incorporates like everything, all built infrastructure, housing, agriculture, and so on and so forth. And the interesting bit is that these reports have highlighted something, that there's a lot of uncertainty in the assessment of transport in particular, which is the focus of my talk, and road networks. There's a lot of uncertainty in the assessment of damages and losses for these systems for large flood events. And the methodology that the government is using in particular, which has been used in these reports from which the numbers come, it does not consider indirect losses in a sufficient way. And what I've shown is a cut snapshot of one of the examples, or the pretty much the methodology that comes from the report from the government, is that their methodology, which shows the methodology and says like the best estimate for cost incurred by road damages and delays. So damages over here means the direct economic damage, which is essentially the physical cost of replacing something. And the indirect losses, which is what I'm focusing on as well in this talk, they refer to them as welfare damages, which are the delays of and disruption costs from big flood events. And what the government methodology assumes is that they generally do a 50-50 split between these. And so in the first instance, even if you don't know anything about flooding or flood impacts, you would question this, like, how come direct damages are same as indirect? So essentially what they're mainly doing is they estimate physical damages, and they just add a multiplication factor to double it. So the indirect welfare damages are mostly the same. So we feel that there's a lack of a tool to measure also these flood impacts at the national scale. And this leads to kind of further discussions and motivation for the study, which kind of a piece of work I did for the National Infrastructure a number of years ago, which was among thinking about resilient infrastructure systems. And this report from the NIC, the National Infrastructure Commission, which came out in 2020. I did a bit of background study which fed into this report. But essentially, one of the recommendations from this report was that regulators should consider some system to regularly stress test infrastructures and deliver this kind of capability to ensure that we have a better understanding of essentially stress testing outcomes, which would then help inform resilience standards of infrastructure services. And they also noted that the gap is understanding these systemic failures, again, these indirect losses in the case of transport or any other network. And there's a gap in understanding these systemic failures, and also there's a lack of coherent data sets and modeling capabilities, which lead to inconsistent risk measures. So we need some sort of kind of things to address all of these. So in order to respond to all of these challenges, the NIRD, which is the National Infrastructure Resilience Demonstrator Project, was conceptualized. I wrote a proposal, and DAFNI was very kind enough to fund it. And the project has a vision. Essentially, there's 3 objectives. It was just concluded early this year in April, but it continues, and I'll come to that later in my presentation. But essentially, our objective is to provide a capability to build some process-based network usage models and stress test these with extreme hazard events, and then model systemic failures to quantify indirect network losses. And the outcome would be some sort of national scale modeling capability and software tool to quantify risk and resilience to extreme hazards. The project has a vision of looking at not just one network, but more interdependent networks and interdependent impacts. I'm going to, in this presentation, concentrate only on one network, but we are, as we speak, kind of expanding this capability through other projects. And DAFNI has been quite instrumental in allowing us to build this first process-based network usage modeling and at large scale, because this itself, even for one infrastructure network, is a huge challenge to overcome. So this is what our project kind of overview objectives and outcomes are. And in particular, I'm going to kind of focus the rest of my talk on how we achieved this in the case of national roads uh, for the project that we just did with DAFNI support and STFC support. So in the case of national roads for the UK, we built a framework, which is shown here in this slide. Essentially, the idea was to build something that is very local scale, and yet it can be scaled up to at the national level. So that's what would make it a national scale model, which is more generalizable. So if you look at the first picture here on the left, which is kind of, we have built some sort of very local model to represent flows of journeys from an origin, which is a node supply point, we call it, to a location of demand, which is a node demand location. And we route it through a road network, and we consider capacities and limits and everything of this road network. And once we build this model, essentially it's a model which tells you how people commute every day through the road network. And once we have done that, then in the middle picture over here, we introduced some flood events on top of it. And we worked with colleagues in JBA, which is a flood, they're a consultancy company that makes flood maps, which is one of the best state-of-the-art flood maps in the UK, which are used extensively in the insurance industry in this country. So we stress test this road network with floods. And one of the things that happens is that once you stress test, you notice direct damages, as if bridges collapse or roads are kind of damaged because of direct floods. And what happens after that is, essentially, if you're traveling around the road network, then you need to essentially reroute your journeys, or some of travel will not be possible. So that is what we are trying to then model, which is the road disruption and rerouting analysis. And this is then followed by outcomes, where we are trying to understand what are the spatial flows along the network and how are people isolated. And we are quantifying the economic damages over in terms of the physical damage costs and also the indirect costs of delays and disruptions. And I'll show that in the rest of my slides. So one of the demonstration, which this is why, I mean, that's why the project is called National Infrastructure Resilience Demonstrator, because it's aimed at demonstrating this. So one of the demonstrations that first we have done is we have actually demonstrated that we have a model that works at the Great Britain scale. And we looked at 2021 Journey to Work statistics, which come from the Office of National Statistics, which were the very latest census statistics that were released. And they released these statistics. They were released for England and Wales. Scotland has its own statistics. So we combine all of them and harmonize them into some sort of journey to work statistics between output areas. And the whole of Great Britain is divided into 235,000 output areas. So imagine if you don't know anything about output areas, it's a very low level of kind of administrative boundaries that involves between 400 households to 2,000 households, I think, at the most. And essentially the whole of Great Britain is divided into 235,000 output areas. So that's a lot of output areas. And across these different output areas, the data tells us this journey to work kind of statistics that tell us how many people are commuting for work from one output area to another output area. And I want to stress is we've used this as a baseline, but the model can be adapted to any other kind of origin test or this journey to work matrix or any matrix that tells you about high-level flow patterns. And from this matrix, we have translated this into 12 million journey to work trips across Great Britain's 82,000 kilometers of motorways, A roads, and B roads. And we have accounted for speed and capacity considerations and account for congestion. I want to note something, that most models that kind of do risk analysis, they don't account for essentially things like speed, capacity, and congestion considerations. Whereas this is always accounted for long-term planning models where people look at these kind of effects. But in risk models, because it's a bit complicated and computationally intensive to do that, so we have tried to overcome that barrier. So one of the results, for example, of this study, as you see over the map over here of the first map on the left, which is in blue, which shows the simulation of our model, which shows the patterns of journeys all across Great Britain. and the map on the right, which is the red one, which shows the comparison of this with observed annual average daily flow. So essentially what we're simulating is an average daily flow of journeys or trips happening for work across the UK, and we are comparing them with passenger flows observations which are released by the Department for Transport. And these are the journey flows of commuting vehicles, cars, pretty much. And so we've kind of done a comparison, and we feel that our model, just the first level of validation is how well are we representing flow patterns across roads in the UK. And we believe that we are doing very well. We are slightly overestimating B roads in our model, because for us, B roads is the most local road which we capture. There are even more local roads in the UK road network. For example, roads which are residential and much more minor. But we haven't gone to that level of classification. But B roads are pretty much the first. So that's why they are kind of more flows are being concentrated on these roads, because we are ignoring some of the minor roads. So that's why we overestimate flows at the more local level, but then at the more higher level, some of them are being underestimated for A roads, which connect major cities together. This I have to note, this overestimation, underestimation is not by too much. So we are mostly getting it very right. So one of the gaps we've addressed through this is that there's no national scale model capability for trip allocation at such a detailed scale at which we are talking about. So our model builds this national scale picture from a very local scale. And then coming to kind of floods. So once we have kind of built this model, and essentially, as I said, uh, we have a model. What the model tells you, like how many people are traveling from A to B, how much time it takes to travel from A to B, and what's the cost of travel in terms of your vehicle operating costs, your value of time, and so on. So it's a cost function in terms of, it gives you the pound value of traveling from A to B. Commuting includes toll costs and all of those along major motorways and everything as well. So essentially, once we have the travel patterns and everything, we wanted to stress test this against some flood events. And what we decided, we wanted to look into known historical flood events, because one of the questions that we got was that stakeholders and most people like to see some sort of narrative that they kind of understand, which is like some past experiences of known floods, because that kind of also helps you kind of say that your model is grounded in some known kind of events and known kind of experiences of people, and also known kind of a quantification of damages and losses that might have been done in previous government reports, or other kind of people can relate to them. Uh, so we looked at some sort of storm event, major flood events, and these are listed over here. They span from flood events all the way from 1953. There was these famous floods in 1953 in the UK, which actually transformed a lot of UK's kind of policy towards kind of flood protection, especially around coastal areas. And then there was a flood event in Easter 1998, which we've looked at. And then, but most of the flood events are more recent, starting from 2007 all the way till 2024, as is listed over here. So one of the things that we are doing is, for each flood event, and this is our colleagues in JBA have created the flood footprint of the flood event. And I say, what I mean by an event over here, I have to clarify what it means. Essentially, the extent of flooding which was seen over a sustained duration of rainfall that was captured over kind of sustained duration of time. So essentially, when we say summer floods of July, so this is capturing the maximum flood depths and the extents recorded for floods that happened across the UK over the month of July, and then mapping their footprint. And the interesting thing is that these maps, they give you the flood extent and the flood depth in meters. And the reason we need this information is the depth tells us how severe the flooding is. And so we can use that depth to stress test our road networks. And just to note over here, because we are kind of simulating flows for 2021 conditions, what we're doing essentially over here is a counterfactual analysis. We cannot simulate flows for 1953. But what we are essentially saying, the argument of what if a flood that happened in 1953 happened in current conditions, or for current for us means 2021 flow conditions, what will be the impacts? And so this has been a very interesting counterfactual analysis that we've done. And we are calling it stress testing essentially because we are simulating these different kind of ways, all these different kind of floods for a general model. So we are essentially throwing floods at it anywhere in the country across a one general flow allocation model that we have built. That's why also it is a stress test. Just to kind of give you a bit of a framework, the computation or the implementation framework that we have built over here, which is the damage and disruption assessment framework. And this flowchart, my colleague Yue has kind of built this. Essentially what it captures, as I said, it captures highlighting the boxes in red, which is it captures the damages and the costs, the physical damages, which come from known like vulnerability curves. I mean, people who work in insurance and in kind of also vulnerability assessments in academia, there are these known vulnerability curves which tell you uh, the cost of damage versus a given flood depth. So we are using that to first infer how much of roads are damaged and bridges are damaged and what is the value of damage. And one of the things what we are doing is there's kind of once you introduce a flood on a road, we are looking at the flood depth at the location of the road, and then looking at some sort of these speed flow reduction curves as well. So one of the first things that we also look at, if a road is flooded, but if it's not damaged, but it's full of water, traffic will be slowed down. There will be speed flow reductions and everything that are imposed. And that will kind of then create a knock-on effect in essentially reducing road capacities, reducing kind of speeds, and kind of adding more capacity constraints to roads. And that will create a disruption chain. And we're also looking at kind of as is disruption. So we look at disruption progressing over time as well as the roads are making recovery. So one of the things what we have done is we have also looked at like day zero of imposing a flood, and then over time how disruption, this recovery might happen, that these roads which are damaged, bridges which are damaged are flooded, are being flooded and then are being repaired. So what I show over here in the box on recovery, which is just a stylized kind of recovery for bridges, which is a straight line, but we have done nonlinear recoveries as well. And for other roads, bridges generally we have assumed take longer to recover, and whereas other roads might recover quickly, and because the drainage and everything, the water might just drain out. So an example of this, just from a demonstration, I'll show you our method for the kind of floods in Scotland example. I'm actually currently sitting in Edinburgh in Scotland, attending a annual conference for a project I'm involved in. That's why I've picked up a Scotland example. So what this shows, a worked example of our case study of our work, is what you see here in yellow is the road network traffic flows that we have mapped. And what you see at the background of this, the satellite imagery, of course, but the blue stuff that you see is the flood map, the flood event of the 2016 floods in Scotland. And as you see, first of all, the first thing you would notice is that these floods are widespread. So we are capturing floods happening over a sustained period of time. So they are local, and yet they are kind of also over a very large area. So what we are capturing is very large disruptions happening over very kind of flooding happening over several parts. Which is what happens in these large-scale flood events that are generally studied. And as you see for the inset figure over here, we can really zoom in. These flood maps are really kind of very fine scaled. They are at actually 5-meter resolution to 10-meter resolution, and it shows like very accurately which roads are flooded and where are the flood concentrations. So the first thing, as I said, is like looking at the damages from the superimposition or the intersection of these roads with kind of the flood map. We are able to identify the roads which are directly intersecting with these floods and what damage they are sustaining. So in the map on the left, I show you the extensive minor and moderate damages of roads. We have numbers for this. Extensive means like the road is pretty much damaged completely. Minor is kind of a reasonably less amount of damage, and moderate is the road might be not exactly damaged, but it might be flooded enough that it might be disrupted. And as you see, this first analysis, if you are kind of looking at if you're a stakeholder, you're kind of just with this information, you can just identify where the locations of vulnerable roads are located. And if you zoom in, you can see, for example, in the zoomed in map, the bridge, especially roads which are like, I think most of the extensive damages we see along these major bridges which are crossing rivers and which are pretty much important kind of critical points along these networks. And our analysis shows that we estimated the direct damages of these floods, 2016 floods in Scotland, to be between 12.3 to 17.7 million pounds. So there's a range of uncertainty because we are considering uncertainty in costs, uncertainty in damage values, and so on and so forth. The bit that kind of we are really interested in looking at the disruption aspect of it, which is essentially what I show here in the map in the left, which is kind of how widespread the disruption is. The map in the left shows the changes in traffic flows. Essentially, what happens after this flood is introduced? Where do the traffic flows increase? Where do the traffic flows decrease? So most of the map you see, it says shades of purple in it. Purple essentially means like these are the roads where the flows have really decreased. So essentially, they are not good for travel, and the flows have been disrupted. But because we are considering rerouting, the flows have to be rerouted. So there are some roads which are kind of getting more traffic. And again, as I said, this considers congestion effects and everything as well. So one of the things this also gives us an understanding is after big floods, there might be this case of looking at which roads absorb more traffic and if these roads should also be kind of fortified to make sure that alternative routes and everything are also available. And a zoomed in version, for example, over here shows like the areas where, as I said, with the bridges and everything which were disrupted, we see a lot of kind of journeys being kind of disrupted in those areas, and most of the traffic flows have to be diverted along different routes which are not affected by the flooding. And this whole effect of kind of rerouting, because there's a lot of journeys happening, every journey has a cost associated with it. Traffic dealers produce more cost. There's a value of time associated with it as well. This all kind of adds up and accrues. And in our model, we are estimating these disruptive impacts to be around 90 to 150 million pounds for this event. And as you see from the map on the big map on the left, these disruptions are much more widespread over a much wider area than where the physical damages happened. Actually, one of the things we noticed is some of the journeys are even longer. They go from Scotland even into Northern England and everything, and some of those trips are also kind of affected and disrupted. But this all adds up, and the numbers are pretty big. Another demonstration quickly is for the 2007 summer floods, which we've studied. And we have three kind of flood maps, which are summer floods over May, or June, or July. And this includes both surface floods and river floods. So the flood maps that we have used, they consider not just one type of flooding, but different types of floods as well. So we are looking at kind of the floods extents and depths across these 3 months and what impacts they created. So one of the kind of demonstrations in terms of the 3 months, and I'm concentrating only on flow changes over here, is that you can see the evolution of how kind of the widespread effects were of the three floods. So in May, most of it is confined, over a smaller area. June and then July is really the biggest, where the lots of roads are affected, lots of trips are delayed, disrupted, and there's a widespread areas of impacts. And you see some urban areas along Birmingham and London and everything, where kind of in July lots of floods happened and lots of kind of this widespread effects were created. And as I said, some of these journeys are long range as well. So effects are much more widespread than where the floods might have actually happened. And this leads to kind of also understanding some isolated passenger flow heat areas, which is like these heat maps essentially show like across May, June, and July, especially as you see in July, lots of people's journeys were isolated, and like essentially people could not travel pretty much, and concentrated along big concentrations like Birmingham, Gloucester and Oxford was also kind of affected by floods in July. And you see from May to June to July, these effects are becoming more and more kind of widespread. So one of our analysis shows kind of these three floods, how bad it and worse it started getting, and how they intensified. So we've done this kind of analysis through these two case studies that I just showed. We've done this for every flood, as I said, like we had 17 floods, historical flood events. We did a stress test of each one of them, estimated these direct and indirect impacts, and did this counterfactual analysis. And this is the result in one graph, which shows in blue the direct impacts, and in pink we show the indirect costs. And this comes back to my original kind of slide in the background, which I said, like the current government methodology, which says like they assume it's a 50-50 split between direct and indirect. And we are trying to kind of essentially show through our analysis the evidence that this is not the case. It depends on type of the flood, and for some floods the indirect impacts are much higher. I have to say some of these results are kind of, we are looking at them. This is kind of some preliminary or still kind of being checked kind of sense check results, but essentially they make sense to us. We've done a lot of sense checking already. And as you see, for something like 2020 Storm Dennis, I mean, there's a huge kind of indirect impact. 27 summer floods in July, as I said, created a lot of indirect impacts. So we are kind of estimating them to be much higher, and the cost going, if you add the indirect on top of the direct, for some of the larger flood events, it goes to the order of billions, and it kind of creates a big magnifying effect. And across all of these events, we have kind of also traced the aggregated effect of journey isolations across historical kind of flood events. And this gives a good picture about historically where floods are happening more and where kind of lots of kind of these hotspots of people's journeys and trips being affected. I mean, you see, of course, the big urban conurbations, but you also see kind of several things outside the big urban conurbations where trips are being affected, and you see the effect being widespread all across the UK. So kind of, yeah, in our model replicates and this information and is so generic that we can stress test any kind of flood event for the across the Great Britain scale for this. Just to kind of look at, like, we're looking at now the validation, comparing with these high-level reports that I showed. It's very difficult, first of all. There's very little evidence, and sometimes you just find these high-level reports give you some big number. So, for example, for the 1953 floods, there's literally no evidence. There's a reported number of multi-sector total direct damage cost, and they report roughly transport to be 433 million so we have kind of all of these numbers, we have put them at 21 pound values, and our estimates is 393 million, so it's close to their estimates. For the 2007 summer floods, our direct damage costs for the May, June, July is 159 million. The government's reported 127 million. Their indirect is there's a huge range of uncertainty. We are reporting on very significantly much higher cost of indirect disruptions for the summer floods of 2007. 2013, 2014, two flood events, we kind of report much higher direct damages and indirect compared to the government estimates. And for the 2015, 2016 floods across all these different kind of flood events, we are very close to the government estimates. So we are kind of coming, in a way, we cannot also exactly get to the values what is being reported, because some of these numbers which are reported from government said they're also for kind of more local roads, in which we are capturing more like A roads, B roads, and motorways. And also kind of they've calculated, added up these across kind of these multiple events, so sometimes it's difficult to compare. But one of the things that we wanted to also do from this research similar is discussion of having more localized and better data collection also to then validate or report losses and damages from flood events that could be validated as well. So we want to start this conversation. So the project outcomes, the outcomes of our project is, like, we have all our work that I just presented. We have just submitted a paper which is openly available, which is under review. So the link over here, essentially, there's a paper called Stress Testing Road Networks, and it's kind of available and open source, but it's being under review, and we've got the first round of reviews, which have been very positive. So we are kind of pretty much revising it and resubmitting it for the next round of journal review, and hopefully it'll be published in a few weeks or months. The DAFNI platform has been quite instrumental in kind of helping us do the project. First of all, DAFNI gives us a good visibility and publicity, which helps me to present in forums like this. And with the DAFNI, what we have done is it has helped us scale this up at a big level. And essentially, we have created this workflow within DAFNI, and this is DAFNI's workflow, which we've kind of visualized. We can kind of create all of our stuff and then upload it into DAFNI as a Docker, and then build a kind of model workflow, and then just implement it and create some kind of results. So that's been quite helpful. So we have kind of uploaded all our data on the DAFNI platform. It exists, all the road network data, the base scenario, the flow simulation outcomes, and the kind of model parameters and all of that stuff we have kind of uploaded. I have to say we cannot upload the flood maps because they are a commercial product from JBA, which is a company. So there's commercial licensing and all of that involved with that. So we can't upload them. Although we have uploaded a synthetic flood map, which comes from JBA, which they agreed that could be shared openly. And then all of our codes and everything are on a GitHub, which again, we can run through the DAFNI framework. Some test kind of cases which we've been able to test and model and produce outputs also exist on the DAFNI platform, and can be kind of looked at. And we are happy that our whole workflow works, and we were able to kind of work through it. And thanks to the DAFNI team for the support they've been giving us. And essentially, this kind of work has all been done with the DAFNI. The project actually officially ended in April or May this year, but it has found further kind of legacy because this kind of work, it was an 18-month project. This kind of work requires more time and then more kind of development as well. So we're actually now working in another kind of initiative within the UK called the Mac Hub, and working in collaboration with another DAFNI, very successful DAFNI funded project called OpenClaim. Essentially, what OpenClaim does is it's a platform to essentially have climate data sets and future scenarios and population data. So what we are trying to do is we are trying to work with them to understand that how this model can also look at future flow changes in the roads networks of the UK, and how future floods can also be introduced. So we are working with the OpenClaim team to look at future population scenarios for 2030, 2050, 2080, and create some flow patterns, again, flow models for UK roads, and then again, stress test them with flood maps for England, Wales, and Scotland, and then understanding kind of this whole NAFRA 2, which is the new flood maps which have come through DEFRA and the government, how kind of they can be used because they have some climate scenarios as well, and how they can be created to give more interesting decision-making outputs. Because most people in the UK who are looking at flood risk assessments and government and policy are using the NAFRA flood maps. So we want to use them as the next step. We are kind of also expanding, or we are involved in a project at the pan-European scale. It's called MIRACA. It's called the Multi-Hazard Risk Assessment Framework for Climate Adaptation. Essentially, it's building a network model for the whole of Europe, and stress testing it for multiple hazards. So a snapshot of that is shown in the map over here. This is, if you can use your imagination, this is a map of Europe. I mean, it looks like Europe to some extent, and kind of roads along Europe and traffic along them. This is a very early version of our output, but we are refining that with more kind of data and everything. So, and also we want to expand that to other networks, multimodal networks of roads, rail, inland model. So what the model that we've built in this study, which is a general model to understand flow allocation from A to B and understanding capacity constraints and costs and everything. And similar problems arise in other networks like railways, inland waterways, and maritime. So we are expanding the model to have cost functions and capacity specific to these other networks. The fundamental model principle is the same. And then within the UK or Great Britain, we are looking at process flow models beyond road networks for electricity transmission and rail networks, We're actually working at present on some of this development. So for electricity, you see the map on the left, is the representation of the transmission grid of the UK and some sort of flow balancing that we are looking at. It has similar concepts of capacity constraints and how supply and demand meets each other under some capacity constraints. So not very dissimilar to doing a allocation from A to B and putting in constraints in that allocation. Railways, again, we are kind of building using railway timetables and everything to build a process frame model. And where we want to move this all towards is some sort of interdependency assessments that we can look at different networks and disruptions within them and across them. So yeah, just to conclude my talk, so the key learnings from our work that we have had is we've developed a national scale road disruption model. We have created kind of workflows for stress testing this road model under different hazard events for some counterfactual analysis. We believe this is useful for improving our understanding of systemic failure impacts and kind of challenging this whole kind of notion of that is of doing a 50-50 split between direct and indirect impacts, which is what government reports are using. So one of the things we are trying to do is talk to people in DFT and other kind of DEFRA and everything through these projects, which we are now doing, to understand whether we can kind of inform their kind of assessments as well. Recently, DAFNI, the DAFNI conference, which was in Sheffield, I did a poster of this work as well, and somebody from the Environment Agency was very interested. We had a very fruitful conversation about our numbers, and they're interested in kind of seeing and following up. So this was quite interesting. And then, of course, as I said, we want to further extend this to synthetic flood events with future climate scenarios. We want to do pan-European analysis or other kind of sectors within the UK as well, and produce similar metrics, which would then help build a truly kind of wider network stress testing framework for Great Britain and other scales as well. And I think that's pretty much my talk. Thanks a lot for the opportunity to present my work. And this is my contact. I'll probably stop over here. And yeah, I'll stop sharing my screen probably so that I can see people. Thanks a lot.
Thank you, Raghav. Yeah, it's really great to see the volume of research that you've done and to learn about how the project's extended into multiple different opportunities. So it would be good to see the outputs of them once the projects get started and up and running. So yeah, thank you for your presentation. There's a few questions in the chat, so I will hand over to Lindsay, who normally does the questions. So yeah, over to you, Lindsay.
No problem. So the first question we have, Raghav, is what are the main factors that account for the different proportion of direct to indirect damages over time? Is it location of the flooding or the severity?
Yeah, thanks a lot, Bethan, for the question. Yeah, I mean it's a combination of essentially the location and the severity, definitely, because this location, the severity in particular kind of essentially tells us how bad the damage is, like in terms of how severe an asset is damaged. So because if it's completely damaged, then it means that it will also be disrupted for a much longer time. If it's not that much damaged, then maybe the roads will just be, water will be there, and then it'll be cleared out. And yeah, of course, the location determines about how busy it is in terms of traffic, like how much of a road is being used. So some of the assumptions that we have taken, the thing that influences a lot of the indirect damages is the damages and the recovery. So we are looking at, when a flood event happens, we look at some recovery over some extended time, over several weeks, and a lot of it, we have looked at a lot of literature and everything. A lot of it is kind of contingent on bridges being damaged and bridges being fixed and recovered, which takes much longer than roads, ordinary road being recovered. So that determines a lot of the direct and indirect being kind of, especially the indirect being much larger in some cases, where lots of those kind of failures and lots of disruptions happen.
Thank you. So the next question that we have is, how does your model reroute traffic away from a flooded road? Is there a systematic way that this is done?
Yes, indeed. Thanks again, Bethan, for the question. Yeah, there is a systematic way. So essentially, we have built this model, as I said, at the Great Britain scale. So the model essentially captures journey flows, journey travel patterns across the whole of Great Britain. So it's in that way, it is systematic in that way that it's a one model that tells you whether you're traveling from Oxford to London or whether you're traveling from Glasgow to Edinburgh. This is how the trips are happening, and these are the costs. So we have collected costs of travel. It's a more generalized cost of travel. We have collected information of toll costs along roads, fuel costs, and all of that stuff. So we have a cost function. So it kind of, first of all, replicates all those journeys, and then takes into account road capacities, congestion charges, even for London and all of that stuff. And then once we introduce the floods, because it's a whole kind of, it looks at the whole network of the UK, then it sees like if you are traveling from Oxford to London and somewhere in between there's a flood, it looks at the alternate route that you could take and how you could be diverted, and looks at also constraints and congestion along those alternate routes. And so in that way, it does it for everywhere, anywhere in the country. So in that way, it is very generic and very systemic.
Perfect, thank you. So the next person is wondering how your cost modeling framework can feed into reverse stress testing for systemic or interconnected risk for insurance or pension sectors. Do you have any idea?
Yeah, it's a very interesting. But so most of these flood maps, first of all, that we've used, they're actually built for the insurance industry. And one of the things we were actually telling JBA that flood maps probably for infrastructure that itself needs a little bit some. We found that there was some kind of, because we helped them correct some of their maps as well. But yeah, essentially this can feed into essentially reverse. I mean, if I understand correctly, by reverse stress testing would essentially mean that how we can get then say like in a particular sector, essentially how much of it that is affected by roads or something. So if you are, so because we are, so if you are kind of essentially, it's essentially who's using the roads pretty much, and what kind of trips are, what kind of people and their journeys are affected, if I understand that correctly. So at present, yeah, we have a bit of a generic understanding of the people traveling from A to B, but we can kind of infer through our models in some, there is more data which we haven't used in terms of essentially what kind of trips are being done in terms of, and what kind of workplace and what kind of purpose of travel people are doing. So essentially, this information is something that we want to incorporate in our next stages of this analysis to also then say like, essentially which sectors might be affected because of people from these sectors, their journeys are affected more because of a disruption or something like that. So it can be done, yes. If I understood that question correctly, I hope I've answered that.
Thank you. So the next question says, from a flooding perspective, how do you account for the temporal evolution of the inundation extent and flood level at the event scale? How do you model the way flooding progresses over time?
Yeah, so one of the things that I, as I said in my presentation, one of the things we are not doing is looking at real-time flood simulation over. I want to make that very clear. So we are not looking at like an hourly evolution of a flood and how that kind of hourly time evolution of that flood happens. That is done by JBA within their model, the people who have built. So the flood maps are built through a whole hydrological process and kind of which has temporal and spatial coherence of the floods, and looks at, but what comes out of the end of this is accumulation of flooding over an extended amount of time, which is what we are interested in. Because what this piece essentially is trying to fit into is looking at large scale kind of floods that have happened over over an extended period of time, and what are their impacts. Because most of the government big studies and reports which come out, they look at these accumulated effects of floods. So the flood model itself can look at those accumulated hourly kind of effects, but what we are actually looking at is more of a daily impact in terms of looking at so what we do is we look at an accumulated flooding over an extended period of time. We impose that on our road networks, and then we assume that that is like day 0 of a flood event, and then our recovery and disruption subsequent is like day 1, day 2, day 3, so on. It's as a daily time scale and looking at that recovery as those roads are fixed over time. But yeah, I would kind of think that our model could also be broken down into some sort of even finer granularity of hourly time scale and everything. One of the things I would know that thing is very computationally intensive, and we would probably not be able to scale that at the Great Britain scale. That would be more localized analysis, which is kind of complicated to do. But yeah, definitely that is something that would influence some of the model outcomes.
The next question, what other networks are you going to focus on in other projects?
Thanks a lot, Akhil, for the question. So as I said, kind of, we are already working on rail networks. So one of the follow-ups of the DAFNI project, and again, thanks to DAFNI for that, is that kind of it has given us some visibility, and the Ministry of Housing and Communities and Local Government, MSCLG, they have a National Infrastructure Systems Tool, NIST, and they're interested a lot in railways and kind of other modes of transport as well. So we are currently working with them in terms of looking at some railway modeling. Although I have to note their interest is not really on the risk side. They're more interested in understanding congestion along networks, but our model can also inform congestion. But we want to kind of do something on stress testing of railways as well. And we are doing that in this Mac Hub project that we have got as well. So yeah, we're looking at railways immediately as the next step, but we, as I said in my slides, we want to look at also at energy networks as well.
Thank you. What threshold do you use to determine bridge damage or even collapse?
Thanks a lot, Wei, for the question. And yeah, I mean, so we have looked at so one of the things for the these, what I did not cover in detail in this talk is these vulnerability or these functions that we've used to initiate a damage. There's a lot of literature out there, and I've been involved recently in a paper that came out of global vulnerability curves and everything. We looked at some of the vulnerability curves which come from these studies, and in the case of bridges, there have been some very good studies from, for example, Maria Pragnaletto, who's in Philadelphia, has done some good studies on UK bridges, and there have been some colleagues from Bristol who have done some very good work as well. So we used their kind of bridge damage curves that they have created, and there are different thresholds for surface water flooding versus river flooding. I don't have the numbers on top of my head, but essentially for surface water flooding, I think if it was like something like close to a meter of flood depth or something, then the bridge is kind of damaged. For river flooding, it was a bit lesser of a threshold, something like half a meter or something like that. But I think it's in our paper. I might have, I can get back to you with the exact numbers.
Thank you. Are you looking for partners to help expand the analysis onto rail? How would they join you, and can DAFNI?
Yeah. I mean, first of all, just reach out to us, definitely. So in terms of partners, I mean, we are working with colleagues in Newcastle already in the Open Claim project to extend some of our analysis. But yeah, I mean, there's a through the MHCLG work, we have been kind of looking at, there have been some rail companies and everything who are also kind of interested. So they're interested in this kind of work. I know that the DAFNI team was looking at railway timetable data and how they could kind of create some sort of framework to take ingest railway timetable information and create some data out of that, which I was involved in some of the DAFNI user groups, and that was a project that you guys were doing. So I would be very interested in the follow-up that, because of the railways, we are also using the railway timetable work as well. So yeah, happy to have conversations on that.
Thank you. Did you come across any data sharing issues with JBA?
So between us and JBA, not exactly, because we actually have very strong working relationships with them. We have worked with them a lot. We know them very well. They're very good friends and colleagues as well. Flood event. Actually, the project scope actually evolved a little bit after discussion with them, because initially the idea was to just use some kind of synthetic flood just as a demonstrator, but then they saw our work, they got really interested. So they were the ones who suggested using the historical flood maps, because they also get a lot of questions from their own stakeholders and insurance sector to look at some sort of, because people, as I said, get a bit of a, they associate more, and they kind of with historical floods that they might have experienced themselves, and they are more kind of, if you show that you have a model that can simulate that and kind of give you some reasonable estimate, nobody expects you to exactly replicate what happened, but essentially if you can show something that is kind of a good representation, that also builds confidence in people. So JBA was the one who kind of suggested to us that we should use the historical flood maps that they have created. That also kind of gives, it's a good marketing of their own product, I have to say. But yeah, sharing of this, as I said, beyond between us two and openly making all of this available. Unfortunately, it's a commercial product and there's a company, so we can't really share that data beyond our project, unfortunately.
Thank you. And I think we just about have time for the last question, which is what components have been considered into the direct and indirect cost estimations? Is the direct cost mainly about the cost of delays?
So what I mean by direct overhead pretty much means the physical cost of damage, the cost of replacement. Essentially, if you have a bridge that is damaged, what is the cost of essentially building it back? Indirect, essentially what I mean over here is the cost of delays and disruptions. So just wanted to clarify. There are further definitions of indirect that go into further economic impacts of supply chains, businesses, and everything. That is not what we mean by indirect. What we mean by indirect overhead is the cost of delays and disruptions. And direct means physical damage costs. Thanks.
Thank you, everybody. I think that's all the questions. I'd just like to thank Raghav again for your presentation. It's been great, and we look forward to continuing to work with you on this project and future projects. For everybody else, the webinar will be saved online and uploaded to the DAFNI website, which will be later on this week, so we can notify everybody that joined. But yeah, thank you all for your time and attending, and have a great day.
Thank you.
Thanks
See
a
you
lot. Thanks a
later.
lot. Bye-bye.
Bye.
For the opportunity.
Thanks.